In this video, we introduce our recent work, CDSBit benchmarking the performance of storage services in cloud-native database system at ByteDance. This work is jointly done by Southern University of Science and Technology and ByteDance. Dr. Bo Tang from Southern University of Science and Technology is the corresponding author. In this work, we focus on the performance benchmarking problem of storage services in cloud-native database system and proposed CDSBit, a learning-based benchmark, which is accurate, flexible, and easy to use. First, we give a background introduction to cloud-native databases. Many companies have implemented their cloud-native databases, like Amazon, Alibaba, ByteDance, and Microsoft. The key idea of these cloud-native databases is to decouple compute and storage tiers. As shown in the right figure, the top application tier includes various applications, for example, Douyin, Xigua Video, and Toutiao. These applications use millions of transactions per second and pass them to the compute tier in the middle. The compute tier includes a primary database kernel for read-write transactions and several replica database kernels for read-only transactions. They handle the transactions and issue I/O workloads, which consist of multiple I/O requests to read and write the data stored in the storage tier. And now, we take a deeper look into the transaction processing of VDB at ByteDance, which leverages the idea of the log as the database. In this figure, the transactions from the top application tier are processed by the primary database kernel in the middle compute tier. Each transaction derives a set of redo logs that record the page modifications. The redo logs are first received by the global redo log buffer and then are persisted at the append-only log store. After that, the redo logs are shipped to the page store for page modifications. As we can see, under this implementation of the log as the database idea, the development of the storage tier is very critical to the overall performance of a cloud-native database. Due to the importance of the storage tier, we are often concerned with how the storage tier will perform under different workloads and how different implementations of the storage tier influences the performance. For example, how about the performance of the storage tier in cloud-native database if the workload TPS doubles? And what is the maximum throughput if a read-write ratio of transactions change significantly? What will happen if we change the techniques in current storage service slightly, for example, applying a new I/O request scheduling strategy? These what-if questions are important to the development of cloud-native databases, but they cannot be answered easily. To answer these questions, we need benchmark tools to generate and execute workloads on the storage tier for performance evaluation. In addition, we want these benchmark tools to generate I/O workloads that are close to real ones, and we want them to be flexible for different scenarios and very easy to use. However, existing benchmarks, as we will present soon, are far from being ideal solutions. Here, we divide existing benchmarks into three large categories: micro benchmarks, macro benchmarks, and tracer pairs. Micro benchmarks, like YCSB, test and measure the performance of a specific component in a system. By using YCSB, we can measure the performance of the storage tier individually. Macro benchmarks, like TPCC, are typically used for evaluating the end-to-end performance of a system. That is to say, the end-to-end performance of a cloud-native database. Tracer pairs can replay traces with high accuracy, but they heavily rely on traces and therefore have very limited usability. We conducted experiments to see how good macro and micro benchmarks are in terms of performance evaluation of the storage tier. Here, we first use YCSB to synthesize workloads and simulate a real workload at ByteDance, VDB OSS. We do so by configuring the knobs of YCSB with our best efforts and generate I/O requests directly on the storage tier. In these two figures, we compare the intensity and burstiness of the I/O workloads of VDB OSS and synthesized by YCSB. We can easily notice that the I/O workloads of VDB OSS is highly bursty. However, YCSB generated steady workloads. This is because the knobs provided by YCSB could not describe burstiness. Then, we use TPCC to simulate another real workload, VDB-Sync, which is less bursty and write-only. Since TPCC generates transactional workloads on the compute tier, to evaluate the performance on the storage tier, we deploy both the compute tier and the storage tier, use the compute tier to obtain the I/O workloads, and execute them on the storage tier. We also configure TPCC with our best efforts to simulate VDB-Sync. We can see that the I/O workloads generated by TPCC is very different from the write-only workloads of VDB-Sync. This is because the specification of TPCC explicitly rules that the workloads generated is always a mixture of read and write transactions. We also compare the distribution of target address, which is in our case segment ID, and the buffer size of the real and synthesized distributions, as well as the joint distribution of these two properties. In these figures, we can see that even with great efforts to configure YSSB and TPCC, the synthesized workloads are still quite different from the real workloads. Therefore, we can conclude that both YCSB and TPCC fail to accurately resemble the real I/O workloads in production environments of cloud-native database systems. The disadvantages of existing solutions are not just about the accuracy. For YSSB, even with the knobs provided in experiments, we can still easily find out characteristics not supported by the knobs, for example, burstiness. It is also not easy to use these benchmarks, considering that it takes effort and experience to configure the knobs correctly. For TPCC, due to the constraints in its specification, for example, transaction types and mixtures, it is not flexible enough to generate some workloads, for example, the read-only one. In addition, to use TPCC, we have to deploy both the storage tier and the compute tier because TPCC runs end-to-end, which introduces auxiliary engineering efforts and affects the usability of TPCC. Tracer pairs are accurate and easy to use since you are only replacing the trace. However, it heavily relies on the traces and cannot be used to answer the what-if questions we mentioned above. In this work, we propose CDS-Bin, a learning-based benchmark for the storage tier of cloud-native databases that achieves accuracy, flexibility, and usability. This is the architecture of CDS-Bin. It consists of two key models, the IOPS sequence estimation model on the left and the joint distribution estimation model on the right. The IOPS sequence estimation model takes the feature of a compute workload as input and predicts the IOPS sequence of the corresponding I/O workload. The joint distribution estimation model estimates the joint distribution of the segment ID and the buffer size of the I/O requests of the corresponding I/O workload. The working procedure of CDS-Bin is as follows. These two models in CDS-Bin are first trained with the features which are extracted from the logs of the real workloads at first. With the trained models, CDS-Bin then takes the features of the expected transaction workloads as inputs and estimates the IOPS sequence and the joint distribution of the desired I/O workloads respectively. CDS-Bin then adapts YSSB to generate and execute the exact I/O requests of the workloads on the storage tier of the cloud-native database for performance evaluation. Here, we briefly introduce the feature embedding of CDS-Bin. For the compute workload, we simply extract from the transaction logs the TPS of each type of transaction. For example, there are 5 types of transactions in TPCC. The TPS of each are 45, 43, 4, 4, and 4. In this case, the feature vector will be 45, 43, 4, 4, and 4. In this way, we can easily express the cases when the intensity or the read-write ratio of the compute workload changes by modifying the TPS of each type of transaction. For the storage workloads, we use IOPS sequence to express the intensity and burstiness and use the joint distribution of segment ID and buffer size for skewness. It is worth noticing that such embedding only records the TPS of each type of transaction, but not the transaction itself. So the models trained for workload A cannot be used to predict workload B. However, in practice, we found that the cost to train models for each workload is rather low and quite acceptable. In the following figures, we evaluate our CDS bin by comparing the workloads it generates with workload we intend to simulate. Ideally, the I/O workloads generated by CDS bin should be close to the target I/O workloads, and we should not take too much effort to do so. First, we compare it against a real I/O workload, VDB-OSS. In this experiment, the real I/O workload comes from executing the VDB-OSS compute workloads on the storage tier. Then, we input the feature vector of this VDB-OSS compute workloads to CDS bin and use it to predict and generate the corresponding I/O workloads. As we can see from both the LPS sequence and the joint distribution, the real and the generated I/O workloads are very similar. For example, similar intensity, burstiness, and skewness of segment ID and buffer size. We also conduct similar experiments for another real I/O workload, VDB-Sync. Again, the real and generated I/O workloads are similar to each other. In the following figures, we elaborate on the good flexibility and ease of use of CDS bin. That is to say, we can use CDS bin to generate I/O workloads for various compute workloads without too much effort. Taking reproducibility and availability into consideration, we verify the good flexibility and ease of use of CDS bin by conducting extensive experiments on TPCC. We compare the estimated I/O workloads with the computed I/O workloads of TPCC with different TPS and different mixtures of 5 types of transactions. In Figure A, we first use the logs from TPCC transactions whose TPS is smaller than 275 as training data and estimated the I/O workloads with TPS greater than 275. Here, W refers to the ratio of new order transaction. In Figure B, we use the TPCC workloads with low write ratios to estimate the I/O workloads with high write ratios. In both figures, the estimated ones from CDS bin are close to the real ones obtained by executing the TPCC workloads, which confirms that the LPS sequence estimation model of CDS bin is flexible enough to generate I/O workloads for different compute workloads with varying features. Then we evaluate the joint distribution estimation model of CDS bin by comparing the joint distributions of the estimated and computed I/O workloads for various TPCC transactions via box plots. In each figure, we use the trained models to estimate the workloads with high TPS, which is denoted as TPS, and high write ratios, which is denoted as ratio. In all 3 figures, the errors are very small, which shows that CDS bin has good flexibility to generate I/O workloads for different compute workloads with varying features. Besides flexibility, these experiments also show that CDS bin is easy to use. During experiments, after the models are trained, the only input from the user is the feature vector of the target workload. We can easily change the values of the input feature vector for different intensity or read-write ratio, which can be used to answer the what-if questions proposed above. Finally, we show that the tail latency of running CDS bin's estimated I/O workloads is significantly closer to the tail latency of running real I/O workloads on VDB compared with the tail latency of running YSSB-generated I/O workloads. We first configure CDS bin and YSSB to generate I/O workloads to simulate the real VDB-OSS workload. Then, we run the real computed I/O workloads, the one estimated by CDS bin and the one from YSSB, on the storage tier and measure the tail latencies. Compared with the tail latency of YSSB-generated I/O workloads, the tail latency of CDS bin's estimated I/O workload is much closer to the real computed ones. Therefore, we know that using CDS bin for performance evaluation gets results that are closer to real performance. To conclude our work, first, we show that isolated performance evaluation of compute and storage tiers is very important in cloud-native database systems. However, both micro-benchmark like YSSB and macro-benchmark like TPCC fail to accurately resemble the real I/O workloads in production environments of cloud-native database. Therefore, we proposed a novel learning-based benchmark, CDS bin, which could evaluate the storage tier with high accuracy, good flexibility, and excellent usability. That's all of our presentation. Thank you.